All right, chapter 11, we're going to start using balanced equations that we learned from previous chapter. And we're going to start doing some chemistry math, I guess. Equation math is another way to talk about it, but the technical word is called stoichiometry. It's just kind of a fancy word to kind of talk about reaction math, or to kind of talk about the amount of reactants or products that we're going to form or possibly form in a reaction. Like, for example, let's say you want to synthesize aspirin. Let's say you are a pharmaceutical company and you want to synthesize aspirin. You don't just arbitrarily just start adding stuff in and hope that you get exactly what you want with the correct yield and all that other stuff. You have to actually calculate and quantitate how much you want. So there's two ingredients that you need in order to make aspirin. And if you, let's say you want to make, I don't know, a ton of it, 1 ton, well, you need to calculate how much of your starting materials you need in order to make 1 ton. You don't just start throwing stuff. The other thing is you need to know how much of each reagent you need. How much of A do I need and how much of B do I need? Because it's going to cost money in order to do this. So if you're actually working at a company, you then have to figure out all of the costs associated with the reaction. We're not going to do any of the cost analysis. If you take an accounting class, you'll learn that part of it. But as far as the how much reagents do I need, that's something that basically this chapter is going to talk about. And then we'll talk about how it can be incorporated in aqueous reactions. So instead of using grams, so notice we're going to once again talk about mole to mole conversions. We've talked about that before, but this time we're going to talk about it in a balanced equation. Mass to mass conversions, we're going to talk about aqueous conversions. So this uses molarity. We're also going to talk about how we can use it in gas equations. Remember, PV equals nRT. You always have to remember moles. If you can get anything into moles, you can get into anything. So if you get something to moles, you can get to mass of it, molecules, atoms, anything you want, moles of another compound. So if we have a gas and we're given the pressure and the volume and the temperature, we can figure out how many moles, and then we can go ahead and use the stoichiometry to also further figure out more information about a reaction. And then we're going to talk about chemical reactions in heat, because this is actually a big thing. If you want to be an engineer, especially a chemical engineer, you kind of have to know how much heat is going to be produced out of a reaction. Most reactions are exothermic. All right, so if you're doing something on very large scale and it's going to create, the amount of heat that the sun creates, you kind of need to know that to say to your engineers, like, hey, maybe we should do this on small scale because we don't want to melt down the entire building or the town because we're creating so much heat. So again, we're going to use heat associated with this equation stoichiometry. Okay, so stoichiometry is a fancy word that refers to the numerical relationship between the amounts of reactants and products. Okay, and everything is based on moles. Always remember moles, moles, moles. All right, here's a chemical equation. All right, 2 moles of carbon monoxide react with 1 mole of O2 to produce 2 moles of CO2. So this is a mole-to-mole conversion. 2 moles of this to 1 mole of oxygen gives me 2 moles of CO2. That's what these balanced equations are telling me. So remember, there's an imaginary 1 right here. These are the moles. So here are some mole-to-mole conversions. 2 moles of CO to 2 moles of CO2. 2 moles of CO to 2 moles of CO2. All right, this converts it. So basically it says that you form twice the amount of moles of CO2 as moles of O2 that you put into the equation. Okay, this is what we're going to be using. These are the mole-to-mole concepts that we're going to be using. So here's kind of a numerical way of doing it. All right, this equation talks about urea. Urea is kind of a waste product that comes from metabolizing our proteins. It takes ammonia and it turns into urea. So basically, here's a balanced equation. 2 moles of ammonia, 1 mole of carbon dioxide form 1 mole of urea and a mole of water. Okay, so calculate the amount of urea that will be produced by the complete reaction of 5.25 moles of ammonia. So if I'm starting with 5.25 moles of ammonia, first of all, how many moles of urea is this going to make? So if I start with 5.25 moles of ammonia, how many moles of urea is going to be formed in the reaction? Well, this is a 2-to-1 ratio. So this number is twice the amount or twice the number of moles as how much urea I have. Okay, so basically you can quickly figure out that you're going to have half the amount of urea. So basically you take 5.25, you divide it by 2, and you find out that you have about 2.63 moles of ammonia. Okay, how does this look mathematically? And then down here it says determine the stoichiometric amount of CO2 if you start with 5.2 moles of urea. Okay, so here's kind of the mathematical conversion. All right, you're starting with 5.25 moles of ammonia. All right, it's a 1-to-2 ratio. 1 mole of ammonia to 2 moles of ammonia to 1 mole of urea. All right, so you have to put them in the correct order so that your moles of ammonia cancels out with moles of ammonia. So basically 5.25 times 1 divided by 2 gives you 2.63. Okay, now for the next one, same thing. If I'm starting with 5.25 moles of ammonia, well, I need to get to moles of CO2. All right, well, I know 2 moles of ammonia is to 1 mole of CO2. How do I know that? There's a 2 here of ammonia and 1 mole of CO2. So it's going to be the exact same thing. I think this is 2.63 moles of CO2. And if you look, they kind of give you the same exact equation. Here's your moles of ammonia. It's a 1-to-2 ratio, and it gives you 2.63 moles. Okay, so that is how you do mole-to-mole conversions with balanced equations. Okay, now how do we do it with mass-to-mass conversions? These problems are mole-to-mole. Let's do mass-to-mass. Well, your mass of one compound so here my mass of A is converted to moles of A, which then I do the mole-to-mole conversion, mole-to-mole, to get to moles of B, which then I use the molar mass of my product to get to mass of B. Okay, so we're using mole-to-mole conversions to get to it. Now this is kind of an easy one because everything is a 1-to-1 to 2 ratio. Okay, so this equation is already balanced for you. Sometimes the equations are not balanced, so you have to make sure that you balance the equation before you do it. Okay, so here's the equation. Nitrous oxide, also known as laughing gas, is commonly used as an anesthetic in dentistry. It is manufactured by heating ammonia nitrate. All right, the balanced equation is, here's the balanced equation. Calculate the mass of ammonium nitrate. So how much of this do I need if I want to produce 10 grams of nitrous oxide? Now, I hope you can see why this is important to know, because if you're trying to form nitrous oxide, you don't just arbitrarily want to put in 1,000 grams, because you might produce so much nitrous oxide that you might, have so much that the patient will die. Okay, you don't want that to happen. So maybe knowing stoichiometry might help you in that, so that you don't go to jail and because you killed your patient. All right. Obviously, I'm exaggerating, making it sound funny, but that's kind of why we do this. Okay, and then it says, and then also determine how much the mass of your water. Okay, so if I want 10 grams of this produced, how much of this do I need to start with? Okay, well, this is a straightforward mole-to-mole ratio. All right, I'll see if I can do it here so that we have room. So I am starting with 10 grams, 10.0 grams of nitrous oxide, which is N2O. Okay. Well, what do I have to do? Anytime you see grams, the first thing in your head should be moles, moles, moles. Get it to moles, then let's figure out what to do from there. Okay, so how do you get anything to moles and grams? Use the molecular weight. So the molecular weight of nitrous oxide is 44.02 grams of N2O is to 1 mole of N2O. Remember, we get that because nitrogen weighs 14. There's 2 of them, it's 28. All right, plus another 16. So that's how you get it. Okay, so grams of nitrous cancels with grams of nitrous. I'm now with moles of nitrous. Now, what do I have to get to? The first part is I have to get to ammonium nitrate. So I used a mole-to-mole conversion. 1 mole of N2, okay? Why is the mole of N2 on the bottom? Because you need to cancel it out with that one. To 1 mole of NH4NO3. Now you might be saying, well, this is a 1-to-1 ratio. Why do I even need to write this? Because I want you to. Okay? Get in the habit of doing the same thing so that when you have a problem where it is important, like part B, you don't have to think about it. You just do it automatically. Okay? Try to learn how to do something one way, and if it works in every single case, you don't have to think about, well, is this the case where I have to use it, or is this the case I don't have to use it? Try to make it as easy as possible for yourself. And then 1 mole of ammonium nitrate weighs, I have here 80.06 grams. So 10 times 1 times 1 times 80.6, all divided by 44.02, you get 18.2 grams of ammonium nitrate. So that means I need to start with, I need to get 18.2 grams of ammonium nitrate. And if I heat that, I will produce 10 grams of nitrous oxide. I won't produce any more, and I won't kill my patient, and I won't have to go to prison. Okay. Let's move on to the next one. The next one is now determine the corresponding mass of water. So if I form 10 grams of nitrous oxide, how many grams of water am I going to produce? Okay. Now, you can actually cheat, okay, because there is a theorem that we learned which says however many grams you start on this side of the equation, you form the exact same amount of grams on this other side of the equation. So you know the answer. So think about it. How many grams of water am I going to produce? If I start with 18.2 grams and 10 grams of it is nitrous oxide, well, you should know automatically the other 8.2 grams must be the water. Okay? This will always work. Okay? It's the conservation of mass law. All right? However much you start with, that's what you end with. However, we're going to prove this. We're going to do it this calculation way so that we get more practice doing this. Okay? So 10 grams of nitrous oxide times 1 mole of nitrous oxide weighs 44.02. Why are we doing this? To get to moles of N2O. This time, it's 1 mole of N2O to 2 moles of water. Why is that? There's a 1 here and there's a 2 here. That's where these numbers are coming from. Times, in this case, water weighs 18.01 grams is to 1 mole of H2O. And if you do this in 3 sig figs, you should get 8.18 grams of water, because it should be in 3 sig figs, but basically it's 8.2. Okay? Both those ways work. Which way do I want for the test? I'll be pretty clear. If I just say to you how much water, you can just clearly do this and say based on the conservation of mass theorem, this always works. But you should also, the whole point is I want to stress this mole to mole concept. This is the new part. And we get this off the balanced equation. Okay? Okay, let me talk about some limitations to this. Okay? And what's called limiting reactants or limiting reagents or excess reactants. Okay? I'm going to do a little imaginary equation here. Let's say you want to make a grilled cheese. Okay? Or a cheese sandwich. Okay? You need to take bread, which we'll call BD, and we're going to add it to a slice of cheese, CH. And you're going to make a bread sandwich. First of all, how many pieces of bread do you usually use for a cheese sandwich? Usually it's 2. So I'm going to do some balanced equations here. And you'll form 2 BDs CH. Okay? If you think about a cheese sandwich, this totally makes sense. 2 pieces of bread, 1 piece of cheese gives you a cheese sandwich. Okay, so it's a 2-to-1 ratio. All right? Let's say I have 6 pieces of bread. All right, and I've got 4 pieces of cheese. So I have 6 pieces of bread and 4 pieces of cheese. What's the maximum number of cheese sandwiches that I can form? What's the maximum number that I can form based off of this? Well, if 2 of these react with 1 of those, so those 2 will react, those 2 will react, and those 2 react. I have consumed all of my bread. I have no more bread left, but I have an extra piece of cheese. So I can make 3 cheese sandwiches, and I will have an extra slice of cheese left over. So the maximum number of cheese sandwiches I can make is 3. Just because I have 4 slices of cheese doesn't mean I can make 4. All right? One of these is limiting the amount of product that I can make. Okay? And the reactant that's limiting it is the bread in this case. So all the bread is consumed, All right, that's the maximum number of that's the max amount of product I can make. All right, even though I have another slice of cheese, I can't make a fourth cheese sandwich. I just have an extra slice of cheese. So the cheese in this case is my excess reactant, and the bread is my limiting reactant. Okay, so my final product, the amount of moles on my final product is based solely on the number of moles of my limiting reagent. It doesn't matter how much excess I have. This is excess. This I have a huge amount. I mean, I can have, a bag full of cheese, but only, 3 slices of bread. It doesn't matter. My slices of bread will limit how much cheese I get. Okay? Let's say I do the same thing, and this time, let's say I've got 6 slices of bread, but only 1 slice of cheese. Okay? What's my limiting reagent? If you said the cheese, you are correct. So, and because I have 1 mole of cheese, this is a 1-to-1 ratio. However many moles of this, that's how many moles of cheese sandwiches I can make. So that's only 1 cheese sandwich, and I have 4 slices of bread left over. That's my excess. That's basically what limiting reagent is. All right. So if you have, so this kind of shows you how to do it. I'm going to kind of show you the way that I like to do it. I feel like this is the way. There are multiple ways to do it. Your book kind of shows you one way. I'm going to show you one way that I think is the easiest way. Okay. So in this reaction, you have nitrogen gas, hydrogen, and ammonia. All right. So you have 35 grams of nitrogen and 12.5 grams of hydrogen. And you want to figure out how many grams of ammonia this will produce. Okay? First of all, can you say that hydrogen is my limiting reagent because this number is smaller than this number? Since 12.5 is smaller than this, my hydrogen must be my limiting reagent. The answer is no, you can't say that. Why do you think? I'm hoping you said because it all depends on the number of moles, not the mass. Mass, guys, I've been trying to teach you all semester, has nothing to do with really anything. All right, it's the moles that mass represents. The moles is what you want. The moles basically is implying how many molecules you have or how many atoms you have. Okay, because guys, here's a perfect example. Doesn't bread weigh less than cheese? Like if I compare 1 slice of bread to 1 slice of cheese, especially if it's a thick piece of cheese, right? Bread weighs way less, okay? But you notice it has nothing to do with the weight of it. It happens to do with how many of them I have, the number of moles that I have, okay? So you need to get out of your mind, it has nothing to do with mass, it's the number of moles. Okay, we're actually gonna find out, guys, that nitrogen is the limiting reagent. Okay, I'm going to show you. So just to kind of show you, this number, just because it's more, doesn't mean that's the limiting reagent. It's the number of moles. Okay, so how do you do this? The question is, how much of this is produced and what's my limiting reagent? Actually, in this case, which is excess reactant? We're going to do both. We're going to find the limiting and the excess and how much is produced. What you do is the same equations that we did in the previous section, okay? You basically take the number of grams of this and convert it to the number of grams of that. You take the number of grams of this, which is 12.5, and you find out how many grams of ammonia is. Whichever one makes the least amount, that's how much you can make. You can't make any more than that. Okay, so let me kind of show you how to do this. You're going to take 35.0 grams of nitrogen, because that's what you're given. Use the molecular weight of nitrogen, all right, which is 28.02 grams of N2 is to 1 mole of N2. And then I got to do mole to mole conversion. 1 mole of N2 is to how many moles of ammonia? And first of all, why am I going to ammonia? Because that's what it's telling me to do. Calculate the mass of ammonia. 2 moles of ammonia. Why is it 2? Because there's a 2 right there. And then 1 mole of ammonia weighs about 17. I got 17.04 grams. Okay, do the math and you get 42.6 grams of nitrogen. I'm sorry, of ammonia. Now let's do the exact same thing with the 12.5 grams of hydrogen. So 12.5 grams of hydrogen times 1 mole of hydrogen is the 2.02. Again, I am doing the same exact problem, the same exact mathematical equation to make things simple. All right, there are different ways of doing this. Your book talks about it. If you would like to do it that way, that's fine. But I'm trying to show you a one-stop shop mathematical equation that works for everything in this equation. I'm sorry, in this chapter. So this is a 2 to 3 ratio. Why is it 2 to 3? There's 3 moles of hydrogen, which is on the bottom because that has to cancel out with this, to 2 moles of ammonia. And ammonia is 17.04 grams to 1 mole of ammonia. And you do this and you get 70.3 grams of ammonia. Okay, so look at this. 12 grams of hydrogen makes 70.3 grams. 35 grams of nitrogen makes 42.6 grams. This number is lower, so this is how much ammonia is produced. Therefore, the nitrogen, guys, is my limiting reagent. Okay, the question asks for the excess, so that means the hydrogen is in excess. Okay, so what's going on here? Okay, I put in 35 grams of nitrogen and 12.5 grams of hydrogen. All right, what happens is I start producing ammonia. Okay, I start producing ammonia. Start producing. As soon as I make 42.6 grams of ammonia, I no longer have any more nitrogen. The nitrogen is all gone. Okay? Nitrogen has been consumed. So all I have left is hydrogen because 12.5 grams makes 70.3 grams. If I had more nitrogen, the excess hydrogen would keep being produced. I'd keep making more and more and more and more and more and more and more. Okay? Well, in fact, we can figure out actually how much hydrogen is produced. All right, well, there's 47.5 grams of reagents on this side, right? 35 plus 12.5, and I produced 42.6, right? So how much hydrogen is left over? Well, you can figure it out by taking your 47.5 and subtracting your 42.6. So there's 4.9 grams of hydrogen left over. That's how much is left over. Okay? If the remainder of this 4.9 grams of hydrogen was consumed, I would then start making 70.3 grams of ammonia. All right? So does this make sense? I hope this makes sense. All right, there's going to be lots of practice problems that I'm going to give you guys and that we will do when we have our review session as well. Okay, so let me just kind of summarize everything just to make sure. For limiting reagent, now this previous problem is not a limiting reagent problem. I'm just basically saying I want 10 grams of this, how much of this do I have to use? Okay, in this case I'm saying, well, I'm using a certain amount of this nitrogen and I'm using a certain amount of the hydrogen, how much of my final product is formed. All right, why don't we stop the video here because I'm going on for a while, and when we come back we will do reaction yield.